we will move on to the next module on matrices. Again, there's a bunch of definitions here initially, which you will have to remember. Well, matrices is simply a rectangular arrangement of numbers. Okay. So if you have a bunch of numbers, and since I said rectangular arrangement, they're arranged in a grid with rows and columns. There are a bunch of rows, there are a bunch of columns, and then you simply put down numbers here. These are number of rows, let's say P, and you have number of columns Q. And for now, let's assume we're only dealing with real numbers. Okay, so you can think of creating a rectangular arrangement of numbers like this between these two square brackets, and you can think of all possible uh, arrangements like that with P rows and Q columns. Okay, and if all of them are real numbers, then that set we represent that set by a representation like this. All this means is this is a set of matrices or a rectangular arrangement of numbers with P rows and Q columns, and each number is a real number. Okay, and effectively there are PQ real numbers in the rectangular grid. Okay, we can have three types of matrices depending on the number of rows and columns. If you have P equals Q, what type of a matrix is it? When the number of rows equals the number of columns, it's called a square matrix. What if P is greater? So what shape does it have? Square is like this. Well, assume that's a square. What if when P is greater than Q? Yes, it'll look like this. Right? These are called tall or skinny. It's called a tall or a skinny matrix. This will look like this. This is called fat or wide matrix. Again, as we saw in the case of vectors, right? There are some special matrices that we will define, that we will often come across. But before that, if you have a square matrix, right? Well, before we go to that, all matrices in the notes and in the lectures, we will use bold caps to represent matrices. Okay, I'll simply write uppercase letters in bold. I'll simply use uppercase letters when I'm writing on the board. Okay, all matrices are represented like this. Right. And because there are these elements in P rows and Q columns, we use again a subscript notation to identify a specific element in a particular row and a particular column. Okay, A, I, J. So if the matrix is represented by an uppercase letter A, the corresponding elements of that matrix will be represented by the lowercase letter. So the elements of this matrix A will be A, small a, with subscript I and J, where I, this is the ith row, this is the element in the ith row, J. Okay, so if I had a matrix like this, and I ask you what is A21, what is A21 here? Yeah, 2, yes. What about A13? That's 0. What about A33? No, it's not defined. This is not this matrix does not have three rows. So this is not possible. So you get the hang of it. Okay. And now look at some. Is the blue visible? Okay, I don't know why. Maybe this. Okay. We look at some useful matrices. The first one is 0. The 0 matrix, and sometimes you might see me write a subscript like this, which essentially means it's a 0 matrix with p rows and q columns. All zeros. Okay, sometimes I might not write this, and it might be clear from the context what is the size of that or shape of that matrix. Okay. Another important one is the identity matrix. Okay. Identity matrix are essentially like 1. What 1 is to real numbers, identity matrices are that for all possible square matrices. Okay, let's say we are talking about a square matrix that is P cross P. Yeah, okay. It's bad. P cross P. Sorry, P cross P. Okay. We will often represent identity matrices with I, and I might just write a subscript P. That simply means it's a P cross P identity matrix. And sometimes I won't write this, and it's clear from the context. What is the shape? Okay. Before we define what the identity matrix is, we'll define one more term called diagonal elements. These are elements of this form, where both the row and the column indices are the same. That means those are the elements along the diagonal of the matrix. Okay, in an identity matrix, all the diagonal elements are 1, and all the off diagonal elements where I is not equal to j are 0. Okay. Now, if I were to ask you to write the I3, what would be I3? Yeah, tell me the elements row wise. 0, 1, 0. That's all. Same for any IP. So this is the identity matrix. You can in general have diagonal matrices. These are, when you say diagonal matrices, these are again only square matrices. Notice that identity matrices are always square matrices. Okay. Okay. Square matrix. Diagonal matrices are 1, where the off diagonal elements are all 0, and the diagonal elements are non-zero. I mean, you can still have 0 elements in the diagonal, but at least one element is non-zero. Okay, and you will often write them. Well, you write it like this, or if you're using maybe MATLAB or Python, you generate a diagonal matrix by simply calling a function called diag, and then listing the n numbers that you want in the matrix, starting from element in the first row, first column, last row, last column. So if this is alpha 1, alpha 2, alpha 3, this will be alpha 1, alpha 2, alpha n. Okay. That's that. Then the other type of matrices that we might come across called triangular matrices, and there are two types here. You can have upper or lower. These are again square matrices. Okay, you say something is an upper triangular matrix if have the matrix, and all the elements below the main diagonal of the matrix are 0. Okay, above it's you have non-zero elements. It's lower triangular. These are non-zero. That's 0. Okay, there are other types as well, which we will come across as and when we when we go through some of the other topics in the course. Okay. We'll now start defining some operations with matrices. First operation we look at is the transpose operation. Okay, we already saw this earlier, but now we will actually define it. Okay, you remember the inner product? Okay, this is the transpose operation. Okay, if you have a matrix A, if I don't say anything, assume it's from P cross Q. Okay, this is a P cross Q matrix. Okay, if you do the transpose operation, we represent the transpose of A as P with superscript A with superscript T. All you do is you swap or convert rows to columns and columns to rows. Again, you know this already, but I'm defining it just for completion. Let's take the same matrix: 4 minus 1 0 2 2 3. This is a 2 cross 3. This is from R2 cross 3. Where is A transpose from? What does it belong to? The rows become columns, columns become rows. If there are two rows here, then A transpose will have 2 columns, and it has 3 columns here. That means A transpose will have 3 rows. So this will be simply flipped. And what will be the elements of A transpose? This was a fat matrix. This will be a tall matrix. What will be the elements? Well, the first row of A becomes the first column of A transpose. Second row becomes the second column, or the other way around. First column becomes the first row, and so on and so on. What is the first row? That's all. Now, if that is the case, right, if matrices are simply rectangular arrangement of numbers, in the last module, we did see a rectangular arrangement of numbers, right? N vectors. They are also rectangular arrangement of numbers, except that the number of columns is 1. So if you remember, this vector was simply written like this: x1, x2, xn, assuming x is, this is from Rn. This is also a rectangular arrangement, with the exception that there are n rows and 1 column. So we always wrote this as an element from Rn. If you're going to use the matrix notation, you can write this as what? Yes, n cross 1. Number of rows, number of columns. Right? You can, but often what we will do is we'll simply drop this cross 1 if it's not needed. Okay, that's x. But if we think of x as a matrix like this, then we've seen that we can do an operation like this. Right? I can ask, what is the transpose of this? And what will that be? Will it be a tall matrix or a fat matrix? It will be fat like this, and that will simply be x1, xn. Okay, and this, if you use the matrix notation, this belongs to what? This belongs to 1 cross n. Okay, this is a single column, that is a single row, and these have special names. These are called matrices with 1 row or 1 column. We will refer to them as a column vector if there is only 1 column, and this will be called a row vector. Okay, and in this course, all vectors that we will deal with are column vectors. Okay, if you want to explicitly represent a row vector, you take, let's say you want to represent uh, a row vector with n elements. You take the corresponding n vector and assume it to be a column vector, and we simply put a transpose. So for us, row vectors will always be represented like this. If you don't see a transpose and this is an n vector, then you know it's a column vector. This is to avoid any ambiguity. Okay? Because if I simply tell you it's an element from Rn and we don't follow this convention, you don't know whether to arrange the elements as a column or arrange them as a row. That is important because later on we'll see that you can actually multiply these two by matrices, but not in any order. The order in which you place the matrix and the n vector matters. Okay, there it's better if we follow this convention and we say all vectors for us are column vectors. Okay. Next one we will do is, as we did for vectors, it's very bad chalk. Scalar multiplication. Again, very simple. If you have a matrix A, okay, and you say you're multiplying it by some scalar real number alpha, then all you're doing is you're taking each element ij of A and multiplying that by alpha. Okay. So in this case, 3 times will simply be, what will this be? This will be 12 plus 3, 0, 6, 6, 9. That's scalar multiplication. And matrix addition. Same thing as we defined in vectors, in n vectors. How did we define the addition operation in n vectors? Well, what is the condition for us to actually add to n vectors or add to vectors? No, but what is the condition? Can I add 3 vector for the 4 vector? Right, both of them have to be n vectors, right? Then it's okay. If you have 2 n vectors, you can add them. And how did we define the addition operation? Well, you simply add the elements corresponding to the same index, right? You do the same thing. You can add 2 matrices only if A and B have the same size. If they differ in the number of rows or columns, then you cannot add them. Okay, and you simply, the ijth element of this matrix, I'll write it like this. Sometimes when you see me write a matrix like this, in parentheses I write ij. That means I'm talking about the ijth element of this, of the matrix resulting from the addition of these two matrices. This will simply be what? Will simply be the sum of the ijth element of A with the ijth element of B. Okay. Again, if that was A and this is B, what is A plus B? What is the first element of A plus B? Okay, 5, 0, 0 is it? Yeah, okay. That's it. That's vector. That's matrix addition. See, in both these cases, right? We started with a vector, well, a matrix from R P cross Q, and when we did the scalar multiplication, what is the shape of the resulting matrix? P cross Q. It's a R. It's a matrix. It's an element from R P cross Q. What about matrix addition? Both these elements are from P cross Q. When you add the two matrices together, where is the resulting matrix from? Okay, all right. Okay. If that is the case, then I ask you this. If you take the set R P cross Q, okay, it's a set, right? And I can ask Because it's a set, I can ask whether or not that set is a vector space, because vector space is a property of a set. Is the set P cross Q a vector space? Given that I've defined matrix scalar multiplication to be like this, matrix addition to be like this, I can ask, is this a vector space? Is it yes or no? What are the conditions for something to be a vector space? No. What? Okay. Fine. Well, that is a consequence of closure. What are the two important properties? 0 is just for you to quickly check. Does P cross Q have the 0 element? R P cross Q? Yes, it does, right? Because this 0 serial number, let's say this matrix has P rows and Q columns, that's a 0 matrix. It is there in that. So 0 is there. If 0 is there, it can be a vector space. It does not mean it is. If it's 0 is not there, then you know it's not a vector space. What is the condition for something to be a vector space? Go back to the sheet. That's why I say always keep the sheet with you if you don't remember. What is the condition for something to be a vector space? No. What do you mean? What do you mean by scalar multiplication? It has to be what? Satisfied. Hey, there is no satisfying, right? I've defined it to be like this. It should be closed under those two. What does being closed under mean? What does it mean to say this set is closed under scalar multiplication? Well, if you take an element from the set and you do scalar multiplication, the resulting element should be in that set. We started with something in RP cross Q. We ended up with something in RP cross Q. That's closed. That means it's closed. Vector addition is also closed. This is in fact right. So this is in fact a vector space. So in principle, somebody had a question about what is a vector last time. In principle, you can call any matrix a vector because it's an element of a vector space. Okay, but we reserve the term vector or for column vectors just to make our life a little easier. But in principle, you can call a matrix a vector as well. Okay. All right. So now we know that all matrices, set of all matrices of a specific shape form a vector space. Okay. Right. Now we've seen scalar multiplication, vector addition, and in fact we saw these in the previous case also, right? For column vectors, for n vectors. Okay. Did we have a multiplication operation between two vectors in the previous module? We did, right? What was that multiplication operation? Where you take two n vectors and you multiply them together. The standard inner product operation was some sort of a multiplication operation. Okay, it turns out that you can define some sort of a multiplication operation between two matrices. Right, and that's what we look at next. Matrix multiplication. Okay, and we'll see that the standard inner product is essentially a special case of the general matrix multiplication rule. If you have two matrices A and B, okay, let's assume A is from P cross R and B is from cross Q. You have two matrices like this. Okay, if you have two matrices like this, then we can define a useful matrix, a multiplication operation like this when we write it as A and B, and the order matters. Okay, B after A. Okay, and when you write it like this, you could say you are post multiplying A by B, or you are pre multiplying B by A. Okay, so where you put A and B matters, and sometimes you might not be able to do the other way around, multiply things the other way around. We can define an operation like this that produces another matrix C. Okay, and the shape of that matrix will simply be, and this matrix will be from cos q. And you are allowed to do this operation only when these two are the same. Okay, if this is R1 and this is R2, this is not possible. Okay, only when okay. So another way to think about this is like this: if you have this matrix, right? This matrix has some rows, has some columns. This matrix has some rows, has some columns. Let me write that. Okay, you can multiply these two together only if the number of columns here match the number of rows here. So this has to match this. Okay, if they don't match, then you cannot multiply. Okay, so here they do match. So if well, we don't know whether we don't know the whether P is greater than R, but for now I'll assume P is greater than R. So A is like this, B has to be like this. Sorry, this has to match this. Only then you can multiply A and B. Okay, in this case can you do BA? Is BA allowed? Well, you check this number of columns here, number of rows here. Do they match? Yes. Well, you can allow only if P and Q are equal. If they are not equal, then you cannot do this. Okay. Right. So that's the first condition. Then, if these two match, right? If they match, imagine that this somehow disappears, and all you're left with is these number of rows and these number of columns, and that's essentially P. So this is whatever is common disappears, and what you're left with is this. Okay. Right. Well, that's okay. This definition only, I mean, whatever I've said here only tells me what we can multiply, what you're allowed to do, and what will result if you do this matrix multiplication operation. I've not said how you'd obtain the elements of C if you know the elements of A and B. I mean, you already know you've done matrix multiplication before. What can we say about the ijth element of C? Okay. How would you find the ijth element of C based on what you remember from your matrix multiplication that you've done before? Well, I'll simply write the definition. Okay, you take the ith row of A and the jth column of B. Okay, and you simply put K here. Okay, if you do this operation, you can find out all the elements of C. Okay, this is essentially the definition. Right? If it were to, let's say it was up to us, we would say this is stupid. We don't want to define matrix multiplication like this. We want to, we want to define matrix multiplication as what we did for addition, right? You are allowed to multiply two matrices only if they have the same shape, and you simply multiply the elements together. That seems like a nice definition and an easy definition to work with. But if you look at this is some strange definition, right? We'll see later on. Of course, and this, if you want to compute the product of a matrix, you simply apply this. But this really does not give us any additional insight as to what is going on. And later on, we'll find that this particular definition of matrix multiplication actually is very natural. Okay? We'll see why that is later on. Right? For now, this is a definition, but we will, of course, in most cases, never apply this, okay? Or never look at this to get an idea of what is going on. Okay? And we will later on see that there are four views of matrix multiplication. Okay, one of the views actually results in this. Okay, we'll come to that later. But before that, instead of taking on this big problem of multiplying a matrix with a matrix, we will first look at maybe multiplying a matrix with a simpler matrix, essentially a column vector or a row vector. So that's what we will start with. Okay. Um, multiplication by a column vector. Or okay. Let's say I have a matrix A. For now, we'll assume it's P cross R. Okay. I want to multiply it by a column vector X. Let's say. What should be the shape of X? What am I allowed to choose? Can I choose any column vector and multiply? Well, let's assume, I mean, we want to, this is a special case of that. Okay, the matrix multiplication rule. So if that is the case, what shape does X have? Given that this is P, sorry, where is X from? What is the shape of X? Assume it's a matrix, even though I'm calling it a vector, it's a matrix with a single column. So how many rows? If it's single column, then of course you know it's cross 1. It has to be R, right? Because this and this have to match. So this is a vector from R, well, R cross 1. And if you multiply this, let's say we get another, well, we'll actually get a matrix, but but it'll turn out that it's a column vector. And what will be the shape of this column vector? Just look at that. Yes, it will be, right. So this is an important thing to remember. If you take a matrix and you post multiply it by a column vector, what you get out of this operation is another column vector. Okay. Now, if you apply this definition, right? Okay, the details are in the notes, so I won't go into the details of how we come to the result. But if you simply apply this rule, because this is the definition of matrix multiplication, what you will find is there is a very nice interpretation that comes out of this operation, this post multiplying a matrix by a column vector. Before that, I forgot to mention something. We'll take a small detour before we come back. This idea of block matrices. That's going to come in handy when we talk about matrix multiplication. Well, we've seen matrices to be a rectangular arrangement of numbers. Block matrices are essentially rectangular arrangement of sub-matrices. Okay, let's say I have a matrix A. Often it's convenient to write a matrix A like this, where the individual elements themselves are smaller matrices. Okay, so whenever you can write a matrix, whenever you write a matrix like this, express a matrix like this, this is called a block matrix. Okay, you often write it like this because it's analytically easier to express it like this, and the way you would, I mean, you could ask, okay, what is the shape of this matrix, and all of that. That might depend on the specific application you're dealing with, and you might often write it like this because you want to emphasize that one part of the matrix actually means something, another part has another meaning, and things like that. Okay, but if you want to express matrix A as a block matrix, and let's assume this is from P cross Q. These are the only. I mean, there are some rules you have to follow. You can't arbitrarily. You can't have these matrices to have arbitrary shapes, completely arbitrary shapes. Okay. The block matrices in a column, all of them must have the same number of columns. Okay, that means the number of columns of B has to match the number of columns of D. And the block matrices you have in a row will have the same number of rows. Okay, so that means the number of rows in B should be equal to the number of rows in C. But the rows of B and D have no relationship. This can be B can have 4 rows. That means C has to have 4 rows, but D can have 105 rows. It doesn't matter. But in a block row, you have all of them have the same number of rows. In a block column, all the elements have the same number of columns. Okay, that's one. Okay, now, okay, let's do it like this. Let's say is now I can, if I want, let's say this has some meaning to me, so I'll take this and I'll say this is my B matrix. If I define this to be B, my C is already defined. Okay, here because this has to be C. But if there are more columns, right, I could have then just said this is C, the another one is D, E, F, right? But the number of rows are fixed for C. This also means the number of columns for D is fixed. This is D, and this is E. Okay. Now, another interesting thing is, okay, what if I want to take the transpose of this matrix? You could ask, okay, if I take the transpose of this, how do I rearrange this block matrix to get the transpose of A? We know that if the individual elements are real numbers, we know how to take the transpose, right? For example, what is the transpose of A? Let's write that down. Because you know the full definition of A, what is the transpose? So, 4, 1, 0, 2, 1, minus 1. Okay. From this, can you tell me what we need to do here with the block matrices so that this definition that you have here in terms of the block matrices, the individual sub matrices, matches with this? Well, let's look at the last one. 3 remains 3. Looks like nothing's changed here. So it looks like maybe this is just C. This is just E. Okay. But D is now here, right? 0 minus 1. But D was a row before. Now it's become a column. Okay. And what was a column here? C has become a row. So it looks like this is transpose. What about A? Well, A looks like this has become like this and this has come down. So that is. So well, nothing's changed here because it only has one element. Okay, transpose of a single scalar is itself. So this is in fact. So all you do is you take the block row, convert it into a block column like this, and you take the transpose of the individual elements. Okay. B equal to E, is it? What do you mean? Well, you can have this. You could have done this. Right? If this was the new matrix, then of course you have another row here, and you'll have, so we can write that down. So this becomes your okay. All right, that's block representation. We've almost run out of time, but I will just finish this. Okay. Now, if I have a matrix A, right, that means I can write the matrix like this. I can write a block representation for the matrix A in terms of the columns of A. Okay. If A is P cross Q, how many columns are there? Q columns. Okay. That means I can write it as A1, A2, AQ. Each of this is a column vector. Okay. And where are these individual column vectors from? Which space? How many elements do these column vectors have? q elements, right? So each of these column vectors ai q, or in fact q cross 1. Okay, this again the convention I'll follow is if a is a matrix uppercase a, smaller case letter with the underbar with subscript means that's the ith column of that matrix. Okay, so ai is the ith column of this matrix capital A. Okay, before I continue, I'll simply define the row and then we'll stop there. Sorry, oh sorry, rp, I'm sorry, yes, this is wrong. P, did you say q? Sorry, that's from p. I mean, if you're not clear, no, just take look at this example. What is the example? Well, I've taken it up. Okay, I can write this as a1, a2, a3 because it's got 3 columns, and each column has 2 elements. Right? I can also similarly write a as, so this is a, okay, I've written a in terms of its columns, but this is a block row. This is a row vector. Each element is in fact another matrix or a vector. Okay, I can also write a as a block column like this, with the first element being the first row of a, second element being the second row of, second element being the second row of a, and so on and so forth. Okay, the convention we'll follow is we already said that rows are represented with the transpose, right? And we will write it like this: ai and how many elements will we have if a is from p cross q? Well, each of this is a row. There are p rows. That means okay. And whenever you see a tilde like this, right, that simply means we are talking about a row of a matrix. Okay, that's a special symbol we've assigned. Okay. Now, where is a I tilde from? What space? Essentially, I'm asking how many elements does it have? Huh? The matrix A is from P cross Q. That means each one of these must have Q elements. Okay. What is okay in this? If A is this, right? What is A1? A1. It's a column. It's this 40. What is A2? 2, 1. What is A3? 1 minus 1. If we write it in terms of its rows, what is A1 tilde? If that is A, what is A1 tilde transpose? Sorry? 40. What is the first row? See, this is the first row of A. Okay, we'll stop here. We're already okay. See, these I want you to go and revise so that tomorrow a lot of our discussion will rely on this. So I want you to be comfortable with this. Okay, so we'll stop here. Okay, and we'll take it up from tomorrow.